Hey, I've been hearing a lot about power electronics and its applications. Can you break it down for me?
Sure, power electronics is a fascinating field that deals with the conversion and control of electrical power using electronic devices. Let's start with the basics. Do you know about the key components used in power electronics?
I've heard about power diodes and thyristors, but I'm not entirely clear on how they differ from regular diodes. Can you explain?
Absolutely. Power diodes are designed to handle higher voltages and currents compared to regular diodes. They're used in applications like rectifying AC to DC power. Thyristors, on the other hand, are more complex. They include devices like SCRs, silicon-controlled rectifiers, and Tri-IACs, which are used for switching and controlling large amounts of power. Does that make sense?
Yes, that helps. So what about power MOSFETs and IGBTs? I've heard they're also important in power electronics.
Great question. Power MOSFETs are known for their high efficiency and fast switching characteristics, making them ideal for applications like power supplies and motor drives. IGBTs, or insulated gate bipolar transistors, combine the best of both BJTs and MOSFETs. They're used in high-power applications like inverters and induction heating systems. Do you see how they differ in terms of application?
I think so. Power MOSFETs are better for fast switching, while IGBTs are better for high-power applications. But what about DC-DC converters? How do they fit into the picture?
DC-DC converters are crucial for converting one DC voltage level to another. For example, a buck converter steps down the voltage while a boost converter steps it up. They're used in everything from portable electronics to renewable energy systems. Have you encountered any specific use cases for DC-DC converters?
I've seen them in solar power systems. They're used to match the voltage levels between the solar panels and the batteries, right?
Exactly. In solar power systems, DC-DC converters ensure that the voltage from the solar panels is optimized for charging the batteries. This is just one example of how power electronics plays a critical role in renewable energy. Speaking of which, have you looked into inverters?
I know inverters convert DC to AC, but I'm not sure about the different types. Can you elaborate?
Sure, there are several types of inverters, including square wave, modified sine wave, and pure sine wave inverters. Pure sine wave inverters are the most advanced and are used in applications where a clean AC signal is crucial, like in sensitive electronic equipment. Modified sine wave inverters are cheaper but can cause issues with some devices. Does that help clarify?
Yes, that makes sense. So, what about the control aspect? How do we manage the power in these systems?
Power control is a key aspect of power electronics. It involves regulating voltage and current levels to ensure efficient energy use. Techniques include feedback loops, modulation, and switching regulators. For example, in a motor control system, you might use PWM, pulse width modulation, to control the speed of the motor. Have you worked with PWM before?
I've heard of PWM, but I'm not entirely sure how it works. Can you explain?
Of course. PWM works by rapidly switching the power on and off to control the average voltage delivered to a device. By varying the width of the pulses, you can control the speed of a motor or the brightness of an LED. It's a very efficient way to control power without dissipating a lot of energy as heat. Does that help?
Yes, that's clearer now. So, what are some emerging trends in power electronics?
One major trend is the move towards wide bandgap semiconductors like silicon carbide, SiC, and gallium nitride, GaN. These materials offer higher efficiency and can operate at higher temperatures and voltages than traditional silicon-based devices. They're being used in everything from electric vehicles to renewable energy systems. Have you come across these materials?
I've heard of GaN in the context of fast chargers for smartphones. Are they also used in larger systems?
Yes, GaN is making waves in both consumer electronics and larger systems. In electric vehicles, for example, GaN-based inverters can significantly improve efficiency and reduce weight. SiC is also being used in high-power applications like solar inverters and industrial motor drives. The adoption of these materials is expected to grow rapidly in the coming years. What do you think about the potential impact of these technologies?
It sounds like they could revolutionize power electronics by making systems more efficient and compact. But are there any challenges with these new materials?
Definitely. One challenge is the cost. Wide bandgap semiconductors are currently more expensive than silicon, though prices are expected to come down as production scales up. Another challenge is thermal management, as these devices can operate at higher temperatures, which requires more robust cooling solutions. Do you see any other potential hurdles?
I can imagine that integrating these new materials into existing systems might require significant redesign. Is that a major issue?
Yes, that's a valid point. Designers need to account for the different electrical and thermal properties of these materials, which can require new circuit topologies and packaging techniques. However, the performance benefits often outweigh the design challenges. For example, in electric vehicles, the improved efficiency can lead to longer battery life and faster charging times. How do you think these advancements will impact the automotive industry?
It seems like they could accelerate the adoption of electric vehicles by addressing some of the current limitations, like range and charging time. But what about renewable energy? How do you see these technologies impacting that sector?
In renewable energy, the higher efficiency of wide bandgap semiconductors can lead to more effective power conversion in solar inverters and wind turbines. This means more energy can be harvested and fed into the grid, making renewable energy systems more cost-effective and reliable. Additionally, the ability to operate at higher temperatures can reduce the need for cooling, which is a significant advantage in large-scale installations. Do you think this could make renewable energy more competitive with traditional energy sources?
Absolutely. If these technologies can reduce costs and improve efficiency, it could make renewable energy a more attractive option for both consumers and businesses. But what about the role of power electronics in energy storage systems? How do they fit into the picture?
Energy storage systems, like batteries, rely heavily on power electronics for managing charge and discharge cycles. Power electronics are used in battery management systems, BMS, to ensure safe and efficient operation. They also play a key role in grid-scale energy storage, where they help balance supply and demand by storing excess energy and releasing it when needed. Have you looked into any specific energy storage technologies?
I've read about lithium-ion batteries, but I'm not sure how power electronics are integrated into them. Can you explain?
Sure. In lithium-ion batteries, power electronics are used in the BMS to monitor cell voltages, temperatures, and currents. They also control the charging process to prevent overcharging and overheating, which can damage the battery. Additionally, power electronics are used in the inverter systems that connect the battery to the grid or to a home's electrical system. This ensures that the stored energy can be used efficiently. Does that help clarify the role of power electronics in energy storage?
Yes, that makes sense. So power electronics are essential for both the operation and integration of energy storage systems. But what about the future? Are there any emerging trends in energy storage that could impact power electronics?
One emerging trend is the development of solid-state batteries, which promise higher energy density and faster charging times compared to traditional lithium-ion batteries. These batteries will require advanced power electronics to manage their unique characteristics. Another trend is the use of supercapacitors in conjunction with batteries to provide rapid bursts of power. This hybrid approach could be particularly useful in applications like electric vehicles and renewable energy systems. What do you think about these developments?
It sounds like these advancements could further enhance the performance and versatility of energy storage systems. But how do you see power electronics evolving to meet these new demands?
Power electronics will need to become more sophisticated to handle the higher voltages and currents associated with these new technologies. This will likely involve the development of new semiconductor materials, as well as more advanced control algorithms. Additionally, there will be a greater emphasis on thermal management and reliability, as these systems will be operating under more demanding conditions. Do you see any other areas where power electronics might need to evolve?
I can imagine that integration with smart grid technologies will be important. How do you see power electronics playing a role in the smart grid?
The smart grid relies heavily on power electronics for managing the flow of electricity and integrating renewable energy sources. Power electronics are used in devices like smart inverters, which can communicate with the grid to adjust their output in real time. They're also used in FACS, flexible AC transmission systems devices, which help stabilize the grid by controlling voltage and current. As the grid becomes more decentralized, the role of power electronics will only become more critical. What do you think about the potential for power electronics to enable a more resilient and flexible grid?
It seems like power electronics will be at the heart of the smart grid, enabling more efficient and reliable energy distribution. But what about the challenges? Are there any potential issues with integrating power electronics into the grid?
One challenge is the potential for harmonic distortion, which can be introduced by power electronic devices. This can affect the quality of the power supply and cause issues for other devices connected to the grid. Another challenge is the need for robust cybersecurity measures, as the smart grid will rely on communication networks that could be vulnerable to attacks. However, these challenges can be addressed through careful design and the use of advanced filtering and protection technologies. Do you see any other potential issues?
I can imagine that the complexity of the grid could make it difficult to manage all these devices. How do you see that being addressed?
That's a great point. The complexity of the grid will require advanced control systems that can coordinate the operation of thousands or even millions of devices. This will likely involve the use of AI and machine learning to optimize the performance of the grid in real time. Additionally, there will be a need for standardized communication protocols to ensure that all devices can work together seamlessly. What do you think about the role of AI in the future of power electronics?
It seems like AI could play a crucial role in managing the complexity of the grid and optimizing the performance of power electronic devices. But what about the impact on jobs? Do you think the increasing use of AI and automation in power electronics will lead to job losses?
That's a valid concern. While AI and automation will certainly change the nature of work in the power electronics industry, they're also likely to create new opportunities. For example, there will be a growing demand for engineers with expertise in AI, machine learning, and data analytics. Additionally, the increased efficiency and reliability of power electronic systems could lead to the creation of new industries and job roles. What's your take on this?
I agree that while some jobs may be displaced, new opportunities will also emerge. It's important for the industry to focus on retraining and upskilling workers to ensure they can take advantage of these new opportunities. But let's shift gears a bit. What about the environmental impact of power electronics? Are there any concerns there?
The environmental impact of power electronics is a complex issue. On one hand, power electronics enable more efficient use of energy, which can reduce greenhouse gas emissions. On the other hand, the production and disposal of electronic components can have environmental consequences, particularly if not managed properly. There's also the issue of e-waste, which is a growing concern. However, the industry is making strides in developing more sustainable materials and recycling technologies. What do you think about the balance between the benefits and environmental impact of power electronics?
It's a delicate balance, but it seems like the benefits of power electronics in terms of energy efficiency and enabling renewable energy outweigh the environmental costs, especially if we can improve recycling and sustainability practices. But what about the future? Where do you see power electronics heading in the next decade?
I think we'll see continued advancements in semiconductor materials, with wide bandgap devices becoming more mainstream. We'll also see greater integration of power electronics with AI and IoT, Internet of Things, technologies, leading to smarter and more efficient systems. Additionally, I expect to see more focus on sustainability, with the development of greener materials and more efficient recycling processes. Overall, the future of power electronics looks very promising. What's your vision for the future?
I agree with your points, and I think we'll also see more innovation in energy storage and grid management, which will be crucial for the transition to a more sustainable energy system. It's an exciting time to be in the field of power electronics.
Absolutely. The potential for innovation and impact is enormous. I'm looking forward to seeing how these technologies evolve and how they'll shape the future of energy and electronics.
Thanks for helping me prepare for my basic electronics exam. Can we start with the basics of electronic components? What are resistors, and how do they work?
Absolutely. Resistors are passive components that limit the flow of electric current in a circuit. They are measured in ohms, omega, which is a unit of resistance. The relationship between voltage, V, current, I, and resistance, R, is given by Ohm's law. V equals IR. Do you understand how to apply Ohm's law in a circuit?
Yes, I think so. If I have a 9 volts battery and a 3 ohms resistor, the current would be 3 amperes, right? What about capacitors? How do they differ from resistors?
Capacitors store and release electrical energy in an electric field. They are measured in farads, F, and are used to filter signals, block DC, and store energy in circuits. Unlike resistors, capacitors allow current to flow briefly when a voltage is applied but then block it. The charge stored in a capacitor is given by Q equals CV, where Q is the charge, C is the capacitance, and V is the voltage. Does that make sense?
Yes, that helps. So, capacitors are used for storing and releasing energy, while resistors control the current flow. What about inductors? How do they work?
Inductors store energy in a magnetic field when current flows through them. They are measured in henries, H, and are used to filter signals, block AC, and store energy. The voltage across an inductor is given by V equals L, di/dt, where L is the inductance, and di/dt is the rate of change of current. Inductors oppose changes in current, which is why they are often used in filtering applications. Do you see the difference between capacitors and inductors?
Yes, capacitors store energy in an electric field and block DC, while inductors store energy in a magnetic field and block AC. What about diodes? How do they work in a circuit?
Diodes are semiconductor devices that allow current to flow in one direction but block it in the other. They are used for rectification, signal mixing, and protection against reverse voltage. The forward voltage drop across a diode is typically around 0.7 volts for silicon diodes. Do you understand how diodes are used in rectifier circuits?
I think so. Diodes are used to convert AC to DC in rectifier circuits. What about transistors? How do they work, and what are the different types?
Transistors are semiconductor devices used to amplify or switch electronic signals. There are two main types: bipolar junction transistors, BJTs, and field effect transistors, FETs. BJTs have three terminals: base, collector, and emitter. They can be NPN or PNP types. FETs have three terminals: gate, source, and drain. They can be N-channel or P-channel types. Do you understand the basic operation of BJTs and FETs?
Yes. BJTs use a small current at the base to control a larger current between the collector and emitter, while FETs use a voltage at the gate to control the current between the source and drain. What about operational amplifiers, op-amps? How do they work?
Op-amps are high-gain differential amplifiers used for amplifying, filtering, and comparing signals. They have two inputs, inverting and non-inverting, and one output. The gain of an op-amp is typically very high, but it can be controlled using feedback. Do you understand the concept of feedback in op-amp circuits?
Yes, feedback is used to control the gain and stability of op-amp circuits. What about digital electronics? Can you explain the basics of logic gates?
Sure. Logic gates are the building blocks of digital circuits. They perform basic logical operations like AND, OR, NOT, NAND, NOR, XOR, and XNOR. Each gate takes one or more binary inputs, 0 or 1, and produces a single binary output based on the logical operation. Do you understand how to use logic gates to build more complex digital circuits?
Yes, I think so. Logic gates can be combined to create circuits like adders, flip-flops, and counters. What about microcontrollers? How do they work, and what are they used for?
Microcontrollers are integrated circuits that contain a processor, memory, and peripherals like timers, I/O ports, and communication interfaces. They are used to control and automate electronic systems. Microcontrollers execute programs stored in their memory to perform specific tasks. Do you understand the basic architecture of a microcontroller?
Yes, microcontrollers have a CPU, memory, and peripherals all on one chip. They are used to control and automate electronic systems. What about sensors and actuators? How do they work in electronic systems?
Sensors convert physical quantities like temperature, light, and pressure into electrical signals that can be processed by electronic circuits. Actuators convert electrical signals into physical actions, like moving a motor or turning on a light. Sensors and actuators are essential for creating interactive and automated electronic systems. Do you understand how to integrate sensors and actuators into a microcontroller-based system?
Yes, Sensors provide input to the microcontroller, which processes the data and sends commands to the actuators to perform actions. What about power supplies? How do they work? And what are the different types?
Power supplies provide the electrical power needed to operate electronic circuits. There are different types of power supplies, including linear regulators, switching regulators, and battery-based systems. Linear regulators provide a stable output voltage but can be inefficient. Switching regulators are more efficient but can introduce noise. Battery-based systems provide portable power but have limited capacity. Do you understand the trade-offs between different types of power supplies?
Yes, I think so. Linear regulators are stable but inefficient, while switching regulators are efficient but can introduce noise. Battery-based systems are portable but have limited capacity. What about safety and protection in electronic circuits? What are some common techniques?
Safety and protection are crucial in electronic circuits. Common techniques include using fuses and circuit breakers to protect against overcurrent, using voltage regulators to protect against overvoltage, and using diodes to protect against reverse voltage. Additionally, grounding and shielding can protect against electromagnetic interference, EMI. Do you understand how to implement these safety and protection techniques in your circuits?
Yes, I think I have a good understanding now. Thanks for walking me through these concepts. I feel more prepared for my exam. Is there anything else I should focus on?
You're welcome. It's great to hear that you feel more prepared.